So we are starting at the bottom of page 3, and we're going to be going over the properties of logarithms. The best way to think about these properties is it's kind of like mad spam. We've got multiplying going on between the bases, we add the exponents. Dividing between the bases, we subtract the exponents. So depending on what's going on with the bases, that's what you're going to do to the exponents. In the same sense, it's sort of the same thing as with logs. If I have multiplication in the answer part of a log, we can expand that to be addition of two logs. So if I'm multiplying in the answer part, I'm adding between the two logs. And it kind of makes sense if you think that this is big animal and the whole thing kind of represents ears, because I am adding kind of the exponential form, and this is what's going on between the answer parts. So we call this process of changing one log into two logs expanding. And we call turning two logs into one log condensing. So we can expand and we can condense. You think of condensing as kind of meaning like compressing. We're trying to take two logs and turn it into a one log expression, whereas expanding, we're trying to take a one log expression and turn it into two logs. So on this page and the next, we're just going to be practicing some of these properties lightly, but these are going to come into play more when we start solving logarithmic equations. So property number 2, if I have division in the answer part of the log, we are going to expand that using subtraction. It's like, all right, yeah, it is kind of like math spam, multiplying, addition, division, subtraction. But this third property is the one that I think feels kind of fake. It's like, are we sure we can do that? Because what this property says is if I have a power in the answer part of the log, I can take that and move it out in front as a coefficient. And what's so weird about that is like, wait, we're just going to take a power and move it to ground level. And sometimes when I show this property, students start trying to do it everywhere. It's like, I'm just going to turn x squared into 2x. You can't move powers down to ground level unless it is contained within a log. And the reason we are able to do this is because of what's going on in the background with exponential form. Logs are a way of rewriting exponents, so this works because of the log. In the same sense, we can also take the coefficient and move it back up as a power of the answer part. So that one's kind of strange, and we'll actually kind of get the opportunity to, I don't want to say prove it because I know you guys do not like that word, but we'll get the opportunity to kind of verify that once we start doing some of the solving problems. So for example, if I have log base 2 of x cubed, that is equal to, if I take that 3 and move it out in front as a coefficient, so 3 log base 2 of x. Or I could take the 3 and move it back up as a power. So these items are all equivalent. Sometimes we like to expand, sometimes we like to condense. The fourth property on here, I would like you to label this one the change of base formula. Change of base formula. So some of you guys have been asking, it's kind of annoying that we can't check ourselves on our graphing problems for logs. Or is there a way I can type a log in my calculator if it's not common log or not natural log? If it's not base 10 and not base E, the change of base formula is a workaround for typing that in on your calculator. How it works is if we have log base answer, and actually you can cross off how they have written the change of base formula. I don't like that notation. We can express this on our calculator as log of the answer over log of the base. So if I have a log with any base, I can use the common log to write this expression, which is equal. So if I have log base 2 of 15, I could type that in on my calculator as common log of 15 over common log of 2. I don't teach the change of base formula explicitly usually, like when we go back to this in pre-calc, just because it's kind of a shortcut for how we solve logs later. So if you want to memorize it, you can, but it's really just the first 3 that you gotta know. So these ones are the big ones. This one is more kind of optional. So we're going to go ahead and turn the page, and we're going to see all of these properties in answer. If you're counting down the minutes, we are going to be doing through example 4. We will not start 8.3 today, so we are just going to be working with these properties. So in example 3, we are going to expand and condense. Well, how do I know which one I'm going to be doing, Mrs. Kyrell? If I want to expand, we want to get as many separate logs as possible. So expand many separate logs. And you guys can't see that. So expand, we want many separate logs, versus condensing, we want one log. So if I look at the first 3 problems, in all 3 of those expressions, we have a single log expression. So what we're going to do on those first 3 is twist it apart or expand it into many separate logs. So on 1, 2, and 3, we are going to expand and kind of pull those apart into separate logs. On the next 3 problems, 4, 5, and 6, we have multiple logs, 2 logs, 2 logs, 3 logs, and we are going to try to squish or condense those together into one. And this is all using those properties on the previous page. So let's start with this first one. And if it helps you, you can put parentheses around those to show that both the x and the y6 are inside that log function. So in this log, we've got division in the answer part. So what operation can we use to twist those apart? Subtraction. So division in the answer part turns into subtraction between the logs. So now instead of 1 log, we have 2 logs separated by subtraction. Now at this point, you may be thinking, that kind of looks like we're done, right? Like we have 2 separate logs now. I have a silly little mnemonic device to help us remember the last step. For expanding, we want everything on the land. Expand everything on the land. What does that mean, Mrs. Cairo? It means that if I have any powers up in the answer part of the log, we want to bring those out in front or to ground level on the land as a coefficient. So this now becomes log x minus 6 log y. And that is as expanded as this expression will go. So we're trying to get as many separate single logs as possible. Moving on to number 2. I would approach this one from a math standpoint first. If I wanted to simplify this expression, we are powering up, so we would multiply each of those powers by 2. So log of a squared, b squared. So what operation do we have in my answer part of this log? Multiplication. So if they're separated by multiplication, we expand using addition. So log of a squared plus log of b squared. So multiplication in the answer part, addition between the logs. Next, expand everything on the land. We want to take those powers and use that weird third rule from the previous page that allows us to move those back in front to the land, to ground level as coefficients. So 2 log A plus 2 log B. And that's expanded. Now, what operation do I have going on in that last one, in the answer part? We've got all multiplication. How many logs are we going to have for this one? 3. 1 for the x, natural log x, separated by addition. 1 for the y, natural log y, and then 1 for the z. Expand everything on the land. We're going to bring that 2 out in front as a coefficient. So natural log x plus natural log y plus 2 natural log of z. Easier than what we did yesterday. Big time. But you can see why, similar to math spam, it is easy to get confused with this. The multiplication is inside the log. We expand it to be addition. And if it's addition between the logs, we condense it using multiplication. So let's go ahead and take a look at number 4. Now on these ones, we are going to need to condense. One of the rules that goes along with condensing is you can't condense with coefficients. So if your log has a number out in front of it, we can't squish those together. It's like, oh, these are separated by addition. I'm just going to squish the x and the y together. It's like, ooh, but what are we going to do with those numbers out in front? Short answer, we can't do anything with them. So what do we need to do with those coefficients? We are going to send them to the clouds. Which means send them to the exponent. So expand everything on the land. Everything is a coefficient on ground level out in front. Versus condensing, we want to send all those coefficients back up to the clouds. So they're opposites of each other. So land and clouds, I don't know if it helps you remember. The pre-calc can seem to like it. So let's go ahead and look at number 4. So we have 2 coefficients. So before I can squish those together, we need to send those coefficients to the clouds. So I'm going to move the 20 back up as a power of the x, making it log base 6 of x to the 20th. And then plus, we're going to send the 5 back up to the clouds as well. So log base 6 of y to the 5th. So now, no more coefficients, so we can condense these. They're separated by addition, so what operation will we use to condense those 2 logs into 1 log? Multiplication. So log base 6 of x to the 20th, y to the 5th. Any questions so far? Let's go ahead and look at number 5. Now here, we do have a coefficient, and it's kind of ambiguous as to whether the coefficient is like 5 or negative 5. As a general rule, I like to leave the sign between the logs, so it's a minus sign, so I'm just going to leave that negative and only put the 5 back up as a power. log base 8 of x minus log base 8 of y to the 5th. So now they're separated by subtraction. So what operation will we use to condense? Division. So the first item goes on the top, the x. Second item, the y5, goes on the bottom. So if you're wondering, well, what would have happened if I had taken that negative with the 5? Having that 5 with a bad attitude, that would send it to the downstairs in that fraction. So it kind of does the same thing, but I think it is a little bit easier to just handle it as a minus sign between the logs. All right, folks, on number 6, we've got 3 separate logs. Ooh, and it's the natural log, log natural. We are going to take the 3, send it to the clouds. The 7, send it to the clouds. The 4 to the clouds. So natural log of x cubed plus natural log of y7 minus natural log of z to the 4th. Now, the first 2 logs are separated by addition. So what operation will we need to do to condense those? Multiplication. So natural log of x cubed, y7, minus natural log of z4. Now, these 2 logs are separated by subtraction. So what operation will we use to condense these? Division with the x cubed, y7 on the top, and the z4 on the bottom. And now we have changed that 3 log expression into a 1 log expression. Now again, if you're wondering why would we ever want to play around with logs like this, why don't we just work with it in the form that's given? Condensing is going to make more sense once we start solving. Expanding is, to be honest, it's more of a calculus thing where you're taking derivatives and limits and integrals where you can turn one big complicated thing into a lot of individual separate things that you can take the derivative of. So the expanding we're not going to do as much with, except for just these basic things, but the condensing will come into play a lot with the solving. So folks, we're going to go ahead and move to example 4. Evaluate using a calculator. So get out your calculators. And I'm going to say round to 3 decimal places, which is the thousandths place. And I know from teaching all the math classes that sometimes we need a refresher on rounding rules. It's probably been a while since you've rounded just because a lot of times in algebra we focus on exact answers. May have done a little bit in geometry, but we're going to brush up on some of our rounding skills. Now on this first one, it says log of 100. What's the base of that log if there's not one written? 10. When you don't have the base explicitly written, it is implied base 10, which is the common log. So if we want to do this on our calculator, we can just hit that log button, which is right next to the 7. That's the common log. We don't need to write the base 10. It's implied. And then 100. You don't have to close off the parenthesis, but for when we start doing some change of base stuff, you might just want to get in the habit of closing it off there. So log base 2 of 100 is 2. Now I said around at 3 decimal places. Do I want you to write 2.000? No. That's a chemistry thing with significant digits, so 2 is all good with me. Now if you were surprised by that going, I thought we were going to get some crazy little decimal, we're going to go back to how we evaluated before we could use our calculator. How do we evaluate 1 log? We put it in exponential form using big base 10. Let's actually just rewrite the problem. Log base 10 of 100 equals x. Big, animal, ears. So the base is 10, the exponent is x, and the answer is 100. Does it make sense that x is 2? It sure does. So then what about the next one? Common log of 15. So we got common log again, which is log base 10. Now, if I try to do that same thing that I was just doing on the previous problem, if I try to actually evaluate that by putting it in exponential form, we would get log base 10, 15 equals x. Big, base 10. Animal, answer is 15. Exponent is x. 10 to the x equals 15. Can I rewrite 15 or 10 as base 5? Your brain's going, well, 5 times 2 is 10. 5 times 3 is 15. Is that the same as taking 5 to the first, or 5 squared, or 5 to the third? No. There is no way I can write those as the same bases. So what do you think that tells us about our answer if we can't solve this nicely? It's probably going to be gross. So let's see what happens when we type common log of 15. Oh, we were right. It's gross. But here's the thing about this gross number. If I plug that in right there for x, 10 to the gross number. Whoops, I didn't do the caret button. That's going to be a problem. There we go. 10 to that gross number. It gives me 15. If you're going, how? How is it doing that? Like, how does that actually work? If you remember, fractional powers represent taking the root of something. So when I have a non-terminating, non-repeating decimal, we got some funny math stuff going on here. So it takes something crazy in order to make this not very friendly item come out to be something that works. So we are going to round this answer to 3 decimal places. So there's 3 places past the decimal. But we look at the 4th digit to see if it bumps it up. What are my bumping up rules? How big does it have to be to bump it up? 5 and above bumps it up. We've got ourselves a 0 here, so is that going to bump us up? Nope. So we're going to say 1.176. Here's a fancy new notation. Squiggly equal sign, that means it's about 1.176. It's just a way of saying, well, that's my answer, but I rounded it. So it's not exactly that, like this whole expanded decimal would technically be the right answer. I'm not going to be picky. You don't have to use the squiggle equal sign. It's just a fun new thing. It's a fancy way of saying I rounded. Now we move into natural log. Now natural log is base E, which we still don't fully understand what that is. It's another non-terminating, non-repeating decimal. So this likely isn't going to come out to be very friendly. So if I type natural log of 12, which natural log is right by the 4. Go ahead and tap that button and type 12. And let's see if we can round this to 3 decimal places. We've got 2.484. The 4th digit is a 9. Does that bump us up? Yep, it bumps the 4 up to a 5. So 2.485. Now the last one. By this one, I would like you to write that this is the change of base formula. So use the change of base formula. Or just use change of base to evaluate. We've got log base 3 of 17. The problem with this is I can't put log base 3 in on my calculator. But the change of base formula is a workaround that says I can take common log of the answer divided by common log of the base, which for this problem would be common log 17 over common log of 3. And when I type that in, that gives me what this is equal to, which should be 2.578, but then the 4th digit is a 9, so that's going to bump up my 8 to be a 9. So 2.579. oops, I don't know why I just wrote a 6. 2.579. Now, if I were you, I'd look at that and go, well, okay, I guess, but how do we really know that that works? Well, if I put this in exponential form, big, animal, ears, my base is 3, my answer is 17, my exponent is x, so if I type 3 to the that gross thing, we do get 17. So it's a little bit mysterious, but it works. Now, if you're wondering to yourself, so how does my calculator do the log? I'm still confused about what a log is. How many of you feel that way right now? It's what even is a log? We know it's a way of rewriting exponential form, but how does my calculator calculate a log? I want you to think about this because this is also a mystery that you've just kind of accepted. Square root of 3. How does my calculator calculate this? We understand division, how my calculator does division, because we can do long division out by hand. We understand the programming that goes into that part of my calculator. How would you describe doing a square root by hand? We've just accepted that square rooting is an operation and that our calculator has the programming to do it. Yeah, we can simplify square roots just fine, but as far as doing square rooting as an operation, the calculator has to do something fancy to evaluate it. Same with logs. We can evaluate logs, we can work with logs, but actually using logging as an operation, we do need our calculator to do. Folks, you are amazing. We have gotten through everything. Pages 1 and 2 are due tonight. If you are done with those, you can start working on #the rest on page 3, which is just the expanding and condensing rules. But we'll probably do some more practice with those at the beginning of class tomorrow.